Today we are going to discuss about the crystal lattice, unit cell, crystal and their classification. So firstly we are going to start what is crystal lattice. You have listened this term before, that the regular arrangement of constituent particles are atoms, ions or molecules. Any of these can be said as constituent particles. So the regular arrangement of constituent particles of a crystalline solid in three dimension is basically called as space lattice or crystal lattice. If in exam the question comes as what is space lattice, so you do not be confused with this term. Space lattice is another name for crystal lattice. So the regularly arranged atoms, ions, molecule in three-dimensional crystalline solid is called as crystal lattice. Here you can see this structure. This structure of NaCl is basically the crystal lattice. And all these points that you can see with the red and a black pen, these all corners are called as lattice point. Lattice point or lattice side. Lattice point or lattice side. You can also represent these points with the bold dots or with the circle. You can just draw with the circles also, like this. You don't want to draw the bold dots, you only can make the circles at the corners like this. These corners, these points are called as lattice point or lattice side. What is this lattice point and lattice side? The space or position occupied by the particles. The space or position occupied by the particles. Which particles? Atoms, ions or molecules in the crystalline solid is called as a lattice point or lattice side. So this structure is basically the crystal lattice. How it forms and what is the arrangement of the atom, we will discuss this later. First you have to understand that what is lattice and what are the lattice points. So this regular arrangement of atom, ions and molecules in a crystalline solid of three-dimensional structure. See, in this figure you can see I have drawn many lattice points here. If you are going to draw the line like this, joining these lattice points together in this way, this is the lattice point in a crystalline lattice and I am joining some points. So you can see here, while joining the specific points, lattice points, I got one unit. That one unit is called as a unit cell. So when we are going to calculate the formula masses of ionic compounds, we take one formula unit from their crystal lattice. That is the same concept that I am discussing here. What is crystal lattice and what is the unit cell? So I am saying regularly arranged constituent particles. You can see all the particles are regularly arranged, having a specific pattern to be arranged in this crystal. There are different forms of a crystal and on those crystalline forms having different type of arrangement of constituent particles. So we will discuss them one by one. So from all the crystal lattice points, if I am taking one unit by joining some specific lattice points, I will got unit cell. Before moving towards the detailed description of a unit cell, I'm going to tell you about some characteristics of crystal lattice. In a crystal lattice, there is a same environment. For example, you are making the crystal lattice of NaCl, sodium chloride, then all the environment of this sodium chloride is same. One lattice point is Na and another lattice point is Cl. Positive, negative ions are arranged in a specific manner in a regular arrangement in one crystal lattice. These red dots are shown Na positive sodium ion, and this black dot is representing chloride ion. Every particle is repeated by lattice point irrespective of its nature. Every particle is represented by lattice point. So every particle in this crystal lattice is represented as a lattice point irrespective of its nature. That what's the nature of that lattice point doesn't matter. All the particles in one crystal lattice is represented as lattice point. This point could be of any atom, any ion, any molecule. You just have to say that this point is lattice point. Doesn't matter what is the nature of this point. Made of repeated unit, crystal lattice is basically made of repeated units called unit cell. As I told you at the above figure here, that this crystal lattice having many lattice point, and if you are going to attach these, join these lattice point, you will get the unit cell, and all the unit cells are repeating again and again and giving you a complete lattice structure, giving you a complete crystal lattice. And these unit cells are arranged in all the directions as a three-dimensional structure. Next, what is unit cell? We are going to discuss it in detail. Unit cell. The smallest part of the crystal lattice has all the characteristics feature of the entire crystal. If I am taking one unit cell from whole crystal lattice, that single crystal unit, the single unit cell having all the characteristics of that crystal lattice. If you are going to understand or identify the characteristics, the properties of complete crystal lattice, and separately you are studying the characteristics, the properties of one unit cell, you will see that both having same characteristics, both having same features, because you are taking that unit cell from a crystal lattice, and that unit cell is a complete structure. That unit cell again and again combining together in a three-dimensional structure with another unit cell and making a complete crystal lattice. For example, you having a wall, and that wall is made up of bricks. When you are combining all the bricks, you will get the wall. So if you are going to identify the characteristics of this wall having the same characteristic feature as you are going to take one brick of this wall. In the same way, crystal lattice and the one unit cell of that crystal lattice having same features, having same characteristics features. Before moving towards the types of a unit cell, I'm going to give you the significant points of this unit cell. Unit cell is basically the smallest block geometrical figure of the crystal. It is the smallest block of that complete crystal lattice and geometrical figure of the crystal. This unit cell having geometry, fixed angles, fixed edges. The entire crystal can be built up by repeating it in three dimensions. As I told you before, if you are repeating this unit, you will get the crystal lattice. When you are going to repeat this unit cell again and again in all the direction as a three-dimensional structure, you will get the complete crystal lattice. It shows the structural properties of a crystal. That single unit cell contains all the properties of the whole crystal lattice. The arrangement of atoms in a unit cell describe their arrangement in whole crystal. When you are going to discuss or to identify the arrangement of atoms in the unit cell, these are the particles, atoms or molecules in the 8 corners. So when you are going to understand the features, the characteristics of these particles in this unit cell, you are able to know all the features, all the characteristics of that whole lattice. The quantitative aspects of crystal lattice are deduced from the size and shape of its unit cell. If you want to calculate the size, the shape of whole crystal lattice, you no need to calculate the size and the shape of whole crystal lattice. If you take one unit of this crystal lattice from the whole crystal lattice, if you are taking just one unit by that one unit, by knowing the size and the shape of that one single unit, you can identify the size and the shape of the whole crystal lattice, because you are taking that one single unit cell from that crystal lattice, and that single unit cell having all the characteristics of the crystal lattice. Next, there are 3 unit cell lengths. Edge lengths. On x-axis, edge length is named as A. Remember, you cannot change the names of these lengths. Always name x-axis as A. Always name x-axis as A. These are the edge lengths. X-axis edge length is named as A. Y-axis edge length is named as B. Z edge length is named as C. You cannot change these names. Yes, you can take these axes at any point. You can take x-axis, y-axis and z-axis at this point. You cannot change their names, but you can take the axis at any of the point of the axis. आप किसी भी point पर axis ले सकते हैं, but you cannot change the names. If you are taking x, y and z axis here, so you have to name x axis as A, y axis as B and z axis as C. And you also cannot change the angles. You have to keep the angle same. Gamma is between z axis and y axis, means edge length A and edge length B. The angle between edge length A and edge length B is named as gamma. The angle between A and B is gamma. The angle between B and C edge length is alpha. And the angle between edge length C and edge length A is named as beta. So always the angles between the edge lengths will same. Between the edge length A and B, the angle is gamma. Between the edge length B and C, the angle is alpha. And between the edge length C and A, the angle is beta. So angles remain same. So you can see here 3 edge lengths A, B and C and 3 interfacial angles, alpha, beta and gamma. So total these are 6. These 6 parameters of an unit cell are called as cell unit dimensions or crystallographic elements. In question, if there is a question about what is unit cell dimension or what is crystallographic element, so you must know that the 3 edge lengths and the 3 interfacial angles of a unit cell are the 6 parameters of the unit cell and are called as unit cell dimension or crystallographic elements. Edge lengths are A, B, C and interfacial angles are alpha, beta and gamma. Between A and B, the angle is gamma. Between B and C, the angle is alpha. And between C and A edge length, the angle is beta. There are 4 types of unit cells. 4 types of unit cell. These 4 types are basically divided into 2 as simple unit cell and centered. Simple unit cell is also called as primitive unit cell and centered unit cell is further divided into 3. Centered, face centered, body centered, end centered. Face center is represented as FC, body center is represented as BC, and end center is represented as EC. This is basically not a part of your syllabus of ALP, but I'm just giving you the idea about the types of the unit cell while I'm discussing about the 7 crystal systems. And you will better understand these systems. So, 4 types of a unit cell: simple unit cell, centered, center is further divided into 3, face centered, body center, end center. So total are 4. 1, face center 2, body center 3, end center 4. So these 4 are the type of unit cell. You can say their names in a sequence: simple unit cell, face center, body center, end center. And you can also divide them first and then say their names, like the unit cell is divided into two: simple unit cell and center is further divided into face centered, body centered, and end center. So next we are going to discuss about the crystals and their classification. Basically crystal system. In this crystal system we are going to explain what is simple unit cell, face centered, body center, and end centered unit cell. In a 7 crystal system, basically what is crystal system? There are 7 crystal system, and what is crystal system? Crystal system may be identified by the dimensions of its unit cell along its 3 edges. Axes are, as we know, A, B, C, and 3 angles between the axes alpha, beta, and delta. So that 3-dimensional unit is basically the crystal system. First crystal system is cubic system. First one is cubic system. Here you can see the cube having 8 corners, having 8 lattice points. At the 8 corners, atom, ions, or particles are present in a simple centered cube. SCC means simple centered cube, the first type of unit cell, simple centered, having 8 identical lattice points: 1, 2, 3, 4, 5, 6, 7, 8. Cubic system having all 4 types of unit cell: simple centered, face centered, body centered, and end centered. Cubic system having all 4 unit cells, all 4 types of unit cells. So here you can see cubic system. Alpha, beta, gamma is equals to 90 degree in simple centered cube, and A, B, C length edges are also equal in simple centered cube. This is the first system of crystal system, cubic system. And the cubic system, all the edge lengths are equal and all the angles are equals to 90 degree. These all alpha, beta, and gamma. Here you can see gamma, alpha, here alpha, and here beta. All these angles are equals to 90 degree. And alpha, A, B, and C, A, B, and C, these edge lengths are equal in cubic system. And the first one is simple centered cube. Next we having a body centered cube. Here in a body centered cube, one lattice point is present at the center. One lattice point is present at the center, and all the 8 lattice points that are present on the 8 corners are in a connection with this point here, with the dotted line represented in a rough sketch. These all 8 identical points, those are existing at the corners of this cube, having a link with the central lattice point, central lattice site. This is called as body centered cube. Body centered cube. One lattice point is present at the center of this cube. Next we having a end centered cube. What is end centered cube? End center means there are 2 lattice points at the 2 corners. One at this corner and other one is at this corner. You can also make these points at here and here. So just you have to take 2 endpoints of this cube. 2 endpoints of the cube contain lattice point, and this is called as end centered cube. End centered cube. End centered cube. Total identical lattice points are 10. In body centered there are 9 identical lattice points, and in end centered cube there are 10 identical lattice points. End means when the end centered unit cell term comes, you must know that, you must remember that there are two lattice points, that those are at the two sides, one at the upper and another at the lower side. Next we having a face centered cube. Here you can see face centered cube. Face centered cube mean at all the faces of this cube having a lattice point. For example, you are sitting in a one room, and that room having how many sides? Four, the walls on that room, and one is the roof and the other one is the ground floor. So total are 6 sides. So here you can see the lattice point, one at this wall, another one is at on the other side of the wall, one on the back wall, and one on the front side of the wall, one lattice point at the roof and one lattice point at the floor. So total 6 lattice points. So face center mean that all the lattice points are facing each other. All the lattice points in that cube are present at all the faces. So total identical lattice points are 14 in a cube. In a face centered cube there are 14 identical lattice points. Must remember, one crystal do not contain all these types. At a time, one crystal contain only one type of unit cell. It may be face centered, it may be end centered, it may be body centered, it may be simple. One crystal do not contain all these 4 types of unit cell. These 4 unit cells, the type of these 4 unit cell, like simple, centered, body centered cube, and center, face centered, are names at Brevis lattice. Brevis lattices. These 4 types of a unit cell are named as Brevis lattices. Next, first we having a cubic system, the crystal in the form of cube. Next we having a tetragonal cubic system. Tetragonal system. Tetragonal system. In a tetragonal system, edge length A is equals to B, but edge length B is not equals to C. So A and B are equal, but B and C are not equal. Here you can see the figure of tetragonal system. This tetragonal system having A and B edge lengths which are same, but B and C are not same. A and B are same, but B and C are not same. Alpha and beta angles are same, but basically all are same in this. Only the difference is of lengths. Alpha, beta is same. Alpha, beta and gamma are 90 degree. Edge length A is equals to edge length B, but edge length B is not equals to edge length C. Edge length A is equals to edge length B, but B is not equals to C. C is little bit longer. And all the angles between them, alpha, beta and gamma, are equal to 90 degree. Here you can see 90 degree, 90 degree, 90 degree. All the angles are 90 degree, but as lengths A and B are equal, B and C are not equal in tetragonal. Cubic crystal system having a many examples like iron, copper, silver, gold, NaCl, NaBr, diamond. These all are the forms of the cubic crystal system. And tetragonal having example tin oxide, manganese oxide, ammonium bromide. So these are the examples of this system. Next we having a orthorhombic system. Orthorhombic crystal system. Orthorhombic crystal system have do not have all the edge lengths same. A, B and C edge lengths are not equal to each other in orthorhombic. Angle alpha beta are equal, but gamma, alpha, beta, gamma, three of them are equals to 90 degree. In orthorhombic, three angles are also equals to 90 degree. Here you can see 90 degree, 90 degree, 90 degree. But the difference is between the edge lengths. Edge length A is not equals to B, B is not equals to C in orthorhombic. But all the angles are 90 degree. Alpha, beta and gamma all are 90 degree, only the difference of their edge lengths. Their edge lengths are not equal. A is not equal to B edge length and B is not equal to C. These three edge lengths are not equal to each other. Next we having monoclinic. Monoclinic. Monoclinic crystal system is the fourth one crystal system. In this crystal system, here you can see the figure. In monoclinic crystal system, edge length A is not equals to B, B is not equals to C. So all the edge length A, B and C are not equal to each other. Angle alpha and gamma are equals to 90 degree, but angle beta is not equals to 90 degree. Here gamma and alpha angles are equals to 90 degree, but the beta angle is not equals to 90 degree. There is some deviation in this angle. So this angle is not equals to 90 degree, but the angle alpha and gamma are equals to 90 degree. In monoclinic crystal system, examples of monoclinic crystal systems are sugar, sulfur, borax, sodium sulfate. So these are the examples. And orthorhombic having example of iodine, rhombic sulfur, barium sulfate, potassium sulfate. So you must learn their edge lengths, learn their angles which are equal and which are not equal, and their example along with the figure. You must know how to draw their figure. Next we having a hexagonal system. Hexagonal crystal system. Now this one is a fifth one. Hexagonal crystal system. In a hexagonal crystal system, edge length A is equals to B, but B is not equals to C. A, B, C, these three are edge lengths. Edge length A will be equals to B, but B is not equals to C. B is not equals to C in hexagonal crystal system. In hexagonal crystal system, alpha and beta angles are 90 degree, but the angle gamma is equals to 120 degree. Here you can see this is the gamma angle which is equals to 120 degree, but the angle alpha and beta are equals to 90 degree. Next we having examples of hexagonal crystal system are graphite, zinc oxide, cadmium sulfate, ice, zinc, cadmium. So these are basically showing the hexagonal crystal. Zinc and cadmium, we also discussed this before, that they having hexagonal crystal system. Graphite, zinc oxide, cadmium sulfate and ice, these are example of hexagonal system. Next we having rhombohedral crystal system. This is the this is the sixth system of crystal system. Rhombohedral is also named as trigonal. Rhombohedral having another name, that is trigonal. In rhombohedral, edge length A, B and C are equal, but there is just the tilt in the cube. Here you can see this is not the straight one, having some deviation. Angle alpha and beta and gamma are slightly greater than 90 degree, because this is not at the lines are not at the right angle. They having some deviation from the angle, that is 90 degree. This angle is not 90 degree, not 90 degree, little bit change in the angle. So little bit higher than 90 degree, greater than 90 degree. Next we having last one. So examples of rhombohedral are bismuth, aluminum oxide, sodium nitrate, potassium nitrate. So these are the example of rhombohedral crystal system. Last one, that is triclinic crystal system. In a triclinic crystal system, edge length A is not equals to B, B is not equals to C, and angle alpha, beta, gamma are also not equals to 90 degrees. So in triclinic, not all the edges are equal and not all the angles are equal to 90 degree. All are different. All the edge lengths A, B and C are not equal and all the angles not equal to 90 degree. All the six parameters are changed in triclinic. Remember, all the six parameter, all the six crystallographic elements are changed in triclinic crystal system. If you having any MCQs related to this, that which one do not having any of the six parameters equal, so you must know that the exam answer is triclinic. Triclinic is the one system that do not having any of the two parameters equal. All the parameters, all the six parameters are not equal. Example of triclinic is boric acid, potassium dichromate, copper sulfate. This is our today's topic about crystal and their classification, unit cell, crystal lattice.